Okay, so let's continue the topic of the upper bound lemma to the last thing I wanted to mention this week, which is about how do you use the spectral gap and this mixing in the original problems of the random walks and groups that I wanted to talk about. Like, for example, we had these questions, like, for example, if you start to consider a random walk like this, where you have the group ZP, and let's say you have a lot of places on this circular group here, and let's say we started from this position, let's say at 0, and we started to move things left and right, like, for example, passing an item from left to the right, and then we could ask, like, what is the probability that, like, after how many steps do we reach this point, for example, here, or like this person, like if there's people sitting on this table and like we want to reach a certain person, or after how many tests it is very likely that every person has reached the item, has got the item at some point, or is it possible to avoid it? Like, what's the probability to avoid this item? Like, for example, if you're passing from left to right, is impossible to think. So at what state, like after how many steps we know that this is like close to random, for example, that we know that there's not too many like possibilities to be at every point. So we can answer to these questions by using the total variation distance, because if you remember, like, for example, if you have the random, let's say this is the distribution is given by the half Dirac 1 plus half Dirac minus 1 by putting this plus 1 with probability half and minus 1 with probability half at the probability distribution, and then we have the random variables Tn, which are distributed according to mu, which are IID. This is the that means that they're distributed on mu that Tj is equal to T with measure mu T for any T in Zp, for any J from 1 to n. Then we can form the random walk. So we can form this random walk xn, which is the state of the item, for example, where we have, if we start, let's say, from 0 in this state at the random walk. So this is our random walk on Zp, and we can then ask the probabilities, like, for example, that if we reach a set A, or A could be an identity, then we could then bound this from above or below by using these expressions. And as I said, like with using, thanks to the upper bound lemma, for example, we can then bound this as like let's say the distance to the uniform over P. Then we can bound this from above. So this is, remember, the Lebesgue measure of A, or the uniform distribution of the uniform measure of A. And then we can bound this by using the upper bound lemma. So this is bounded above by the total variation distance to n, because this here is the mu star n of A, the probability of A. And then you have the uniform distribution. And then by the upper bound lemma, we can then bound this from above by using the half of the square root of k or Zp, and k not equal to 0 with the Fourier transform of k to the power 2n. So that's the statement. So how would we like get maybe answers to some of these questions that we have, that after how many steps? So the main thing or the main difficulty is then to estimate this Fourier transform, to get like some proper estimates. So what we can do here, I write this theorem, which is, I think I had it in the notes, that if I have a p at least 7, which is odd, so it's an odd number. I'm just doing it in this case, that if you have the, in the case of odd, and we have this mu is this half Dirac 1 plus half Dirac minus 1 in Zp. So we have these things, and what else do we have? That then we have for any n at least p to the power 2. We know that the total variation distance of n is lambda is at most e to the power minus alpha n divided by p squared for alpha equals, let's call it pi squared over 2. And we have that for any and also we have the lower bound that d mu star n lambda is also bounded from below by 1/2 square root of p. I think I have this, and then e to the power minus alpha n p squared, the same thing, but then you have minus some beta n divided by t to the power 4 for beta, which is pi to the power 4 divided by 11. So it's like a very quantitative estimate. So it's basically the way you get these estimates is by upper bound lemma of this type, and then the lower bound lemma, which was also bound from below for this distance, which basically means that you need to construct a proper set that you have to write a lower bound. But in this case, you bound the Fourier transform in this way to get this expression. And let's prove the upper bound here. So the way this is useful is because now this gives you quantitative estimates. You can maybe ask, for example, after how many steps, for example, this is, let's say, less than 1/100. You could, for example, ask what is the probability that xn, let's say, reaches a person, I don't know, I don't know, let's call it S, for example. Then you could bound this from above by like you could ask, like, when is this, let's say, less than 100, the probability is very small. Then using this this estimate here, the total variation distance and the distance to uniform, you could then ask that, okay, if n is large enough, then this probability is very, very, very small in this way. So you could then find the smallest n, for example, when this is less than 1/100 in this way. So let's prove this is the upper bound. It comes as follows. So we can do it as, in a very simple way. So as we did before, we computed the Fourier transform of this. We've done it a few times already. So it's cosine 2 pi k over p. And then what you have here is then, once you have to compute the Fourier transform, then the upper bound lemma gives the upper bound lemma gives you that if you take mu star n lambda and take that squared, we have this is at most 1/4 some k in zp, k not equal to 0, and then you have the cosine 2 pi k over p to the power 2n. So that was the upper bound lemma. I'm just taking the square root out of the whole expression. And once you do now this, that if you can use that as this p minus 1/2 is an integer, as the piece is odd, so it is the only place you use the oddness of the number, we can actually rearrange this summation here. So when you have this k from, actually this is k from 1 to p minus 1, because the 0th term is not included, and then you take the cosine 2 pi k over p, 2n, then we can actually rearrange the summations on the positive points to going to the half of the points and the other half of the points, and we can actually write this without the pi. So we get the 1 to p minus 1/2, so this is an integer, and take the 2 here and cosine of pi k over p. So have a think about this, why this is true, but basically it's around the thing that you're like basically overcounting. You're summing the same expression twice. When you go through the pi of the expressions, you can see that you're going to pi here over summing over the all expressions. And the reason I wanted to do this is just because now we have for any x which is in 0 and pi over 2, we have because now it's in this kind of a range, we have that the cosine x can be bounded from above. If you take the, take the cosine x, is bounded from above by e to the power minus x squared over 2. We bound this with this Gaussian function in this range. So this is like an estimate you can do, for example, using Taylor series of the cosine around 0, or other like derivative estimates. You can prove this, and then you can apply it in this estimate over here. So apply it on above here, which gives you then the following estimate. This is bounded from above by, if you take 2 here, actually let's put it instead of that one, let's open up this expression here. If you combine these all things together, then we get that this whole expression above here, which includes the cosine. If we use the rearranging and the number 2 that comes from here, we get a half, and then you have the summation from k from 1 to p minus 1 over 2, and then cosine pi k over p to n, and that's bounded now above by half of summation from k from 1 to p minus 1 over 2, e to the power minus pi squared k squared n over p squared. That comes from the fact that we have the x squared here, and then we take this whole expression squared. So that's how the p squared like appeared there. Okay, so then you can continue this when you open the summation. You can get it into a geometric series, and that's how you can then complete the expression. So I have the rest of the proof in the notes, and you can see that then using this expression, using geometric sum, we get that this is bounded above by the statement that we have, that this becomes e to the power minus alpha n over p squared, as we were claiming. So so that's all I wanted to say for this time. And so the next time I want to go a little bit more into the more general groups, for example, and then like show that how these ideas like further along go into the next statement. So like here, as I mentioned, like you get this like very quantitative estimates for computing the probabilities of these expressions. Like for example, in here with this alpha, you get this like after n p squared steps. This is like a very small expression by then taking like the suitable n that this is, let's say, less than 1 over 100 or something like this. You can do the same thing in a more general group, for example, to get like an expression, for example, in the symmetric group, where we would like to study the distance to the uniform in the symmetric group setting. And in that setting, we get the same type of a proof idea, and we get same kind of a theorems in like we have here. But then the problem is that we have to somehow replace the Fourier analysis somehow. So so in the next time, I will go into the more general groups and try to like give you like an idea how the actually the methods differ at some points of the arguments we have done here. So that's all for today, and I'll see you next time on the next lecture on the more general groups.